Good afternoon, everyone, and thank you for coming to the thesis defense of Aviv. Aviv has been a PhD student in my group, uh, and the first time I recall talking with Aviv was it was visit days of 2020, and then Aviv was volunteering for visit day events, and then she approached me and said that let's discuss if there's something exciting to do together. And I think at that point, we was, working with, graph networks and trying to impose structure in machine learning. And I think she has, stood true to her values that, we need something more than just data to help us develop, truly generalizable systems. Then moving from, graph models, she came up with these techniques called as transduction, which allows us to go after distribution, then extending those ideas to inferring human intentions, again, in context of OOD. And then finally also, going to different fields like material science and showing that her work is still, valid. And, it gives good results. So I think in some ways, the field has gone to a different direction where everyone is trying to scale with data, but Aviv has been brave and, stood her stead in trying to say data is not all that we need. So I'm very excited, Aviv, for everything that you have accomplished and hopefully everything that you would accomplish in the future. But of course, I can't say anything about what the outcome of this defense is going to be. So things do have to wait a little. But I thought I'll share maybe a couple of photos, that I have, of you. And when we started, it became COVID. It did mean that I did have to. Oh, this is not my laptop. Sorry. Yeah, so this is one of our lab retreats, and I think this is one of our first photos. I have of Aviv. This is again the same lab retreat, but this is how the group started, and this is Aviv happy after a hike. And I hope this, happiness continued, throughout your research, and very much looking forward to your talk, Avi. So the floor is yours. Please take it away.
Thank you, Pulkit, for the kind introduction, and thank you everyone for being here today. And I'll talk about some work on generalization under distribution shift. So, like Pulkit mentioned, I like to think of what can we do with little data. So even though we have made amazing progress in AI and machine learning, there's still a lot of edge cases, and sometimes a car can still crash into a truck just because it's upside down and not in the training and distribution. So we could maybe cover all of these edge cases and weird scenarios with a lot of data if we keep collecting, but it may take a lot of time and a lot of effort. And there has been a lot of effort in autonomous driving over 30 years. It's estimated that Tesla has billions of data points, and we still sometimes see failure cases. So what can we do? I guess the trend is still data collection, even though we have these problems. And large data collection efforts, so people use the internet data or data that's collected in the real world, like in autonomous driving, and people use simulated data, like in robotics. And now the trend is to generate synthetic data. And sure, maybe one day it will cover everything, but I think there are two main challenges. So I think there's still the issue of transfer and then the issue of adaptation. So for transfer, even though we have so much data with autonomous driving, if we want to now deploy a Waymo in a new city, we have to collect a lot more data and train more, and it's not immediate. And sometimes it's harder to collect data, like in domains like medicine or sciences, when we don't have a lot of high quality data, or when we actually care about being very, very precise. Then in adaptation, if we have robots that are trained in some factory and then eventually deployed in someone's home, we want them to be able to adapt to specific users and what they want, which is not necessarily in the training data. So to summarize, while large data efforts are great, I still think there's work to be done with transfer and adaptation, and maybe we can do well with the data we have, which is kind of complementary to the approaches that scale data and compute. Okay, so today I'll talk about some work that does this. So first, a small overview of the distribution shifts that I've been thinking about. So I'll start with a distribution shift in the task. So let's say we have certain tasks that we've seen during training, and then at test time, we'd like to adapt to a new task. We're going to use inverse generative models to do this. And then once we learn the task, we're going to deploy them when the environment is changing. So this is a type of shift in the input data to the model, which is also known as covariate shift, when the distribution over the data is changing, but the output condition on the input is not changing. Then I'll talk about another approach for covariate shift, which is zero shot. We call this bilinear transduction. And then finally, I will talk about how we applied this to a material science setting and where the distribution shift was actually in the labels, in the output that we were trying to predict. Okay, so for few-shot task learning through inverse modeling, we assume that we get a lot of demonstrations of different tasks. It's a bit choppy, but these are driving scenarios like highway and exit and merge and intersection. And we also assume that we have labels for these tasks. So someone is giving us a natural language label, merge, exit, highway, intersection. And then at test time, someone is giving us a new scenario, roundabout, where it's unlabeled. We don't have the natural language describing what that scenario is. And we want to infer some kind of task representation for that new scenario, just from a few demonstrations. Okay, so usually how people would approach this is do some fine tuning, collect a lot of data of the new task, and also label data of that new task. And then another approach is represent the task by doing some kind of self-supervised learning based on trajectories and finding a latent task representation. And then another approach is in-context learning, where we represent the task by the demonstrations. So we can represent a task with a policy, a self-supervised learned vector, or the demonstrations themselves. And each of these have certain issues. So, So in behavior cloning, again, we would need a lot of data and we could lack generalization because it is very sensitive to covariate shift. And in VAEs, if we do some kind of self-supervised learning scheme like that, we might learn representations that are not that meaningful or that collapse. And in the in-context learning, this is usually good for short horizon trajectories, but not really for long horizons. Okay, so we were inspired by computer vision work where visual concepts are learned. So given a few images or demonstrations of a new concept, in this case, some sculpture, learning a representation then allows to generate images of that new object in different settings. For example, Elmo sitting like that sculpture. And other work has, in computer vision, learned visual concepts as composition. So these kitchen scenarios were decomposed into different components that capture lighting and kitchen island, for example. So inspired by this, we use a generative model to infer a task representation instead of a visual concept representation. Okay, so again, in our driving example, we have all these highway and intersection scenarios. And now we have this roundabout scenario. And we see that if we compare it to baseline, so if we try to infer this roundabout scenario with behavior cloning or in-context learning, behavior cloning it fails pretty quickly, probably due to covariate shift. In-context learning, the car kind of stops in the middle of the roundabout. It's doing well for a short horizon, not for a long horizon. And then ours on the right, we can kind of do roundabout and get to the end of to the road. Okay. Now, how does this work? So this is another example where we did real world tabletop manipulation tasks, and we had some pick and place and pushing tasks. And then our test task, which was unlabeled, was pushing on an elevated surface. And we have pushing on the table surface in the training data. So pushing on an elevated surface is still kind of close, but we'll see that even though it's close, we can't actually perform this task without additional inference. Okay, so our goal, given this new task that is unlabeled, is to find a representation for the task, given the demonstration. And what we do is we use a generative model, specifically a diffusion model, and we input the initial state of the environment, so the first image in the sequence, and some proprioception information and the task representation, which is C. And during training, these are T5 embeddings of the language descriptions of the task. And we output the trajectories. And then we're training this with a normal diffusion objective, which is noise estimation. Then at test time, we only get demonstrations of the new task, and our goal is to find the representation, C tilde. So now we have the same model and we freeze it. We don't train the weights anymore. And instead, we're inputting some random noise initial C vector, the initial state of the environment, and we're outputting some trajectory. We compare that to the demonstrated trajectories using mean squared error, and then back propagate to update the task representation. And then what we get is that if we try to evaluate our model in the training scenario of pushing on a table, then that does well, because we've seen that during training. But then if we go into the test environment where we have elevated pushing, but input into the model the representation of pushing from the training, then it will fail, even though it's still pushing, but the distribution shift is now that it's on an elevated surface. And then if we actually learn a representation for a new scenario, and then input that into the model in the test scenario, we succeed. Another domain is motion capture, where we had dozens of different actions. So jumping, marching, walking. Fortunately, this is a bit slow, but you can probably imagine. And then we have an initial state and a task representation, which again, T5 embedding of, let's say, jump. And then at test time, we want to learn this new action, jumping jacks. So once we learn jumping jacks, we can then generate jumping jacks with our learned representation from a new initial state. And we can also compose it with a training task. So if we compose the jumping jacks representation with walking, we can generate motion of someone who has hands that are doing jumping jack motions and the feet are walking. Okay, so generative models or diffusion models give us this power of compositionality where after we learn a task, we can then generate compositions of tasks. So we can generate tasks on initial states that are different. So that gives us diversity, and then combining it with other tasks that also gives us diversity. But now the other cool thing about compositionality is that we could also use it for learning. So I talked about how we learn one latent vector that represents the new task, but actually we can also learn a linear combination of vectors representing that task. And these vectors don't have to be explicit training points. So in the mocap example, jumping jacks is not an explicit combination of the training motion. But when we plot it as T and E, and we look at the training tasks in blue and orange are the test tasks that we learned, every pair composed represents one task, then we see that they kind of fall in the space of training tasks. So they don't have to be exact explicit training tasks, but if they fall in that space, then their composition could generate something that is a bit out of distribution, like jumping jacks is compared to walking. Okay, and then finally, there's a question of, so where does this come from? Because usually we see this kind of compositional behavior in large models, and we are training our diffusion models on some tasks, but usually not more than hundreds or thousands of demos. And then the intuition is that it's probably a big part of it is coming from the fact that we use T5 embeddings during training, and that model was trained on a lot of data. So during training, our task space had some structure in it. So where will this be useful? Hopefully, eventually, maybe in the future. So if we have a robot that is training on a bunch of tasks in a factory, and then it is deployed in a home, and that person has very specific instructions that were not seen in the factory, and also has a very different environment in their home and very different setups, then learning that task from a human that demonstrates it a few times, and then actually performing that task in a changing house would be helpful, without having to So that's another important point without having to actually fine tune the model or change the weights. Okay. So just to conclude, so generative models enable the following, so we can learn these tasks without retraining, and we can learn them as compositions, and then we can also perform these in new initial states and also compose these tasks with other tasks. So we can here make a few demonstrations go a long way, but what if we didn't have new demonstrations at all in the new environment? Okay, so this brings me to the second part, which is learning to extrapolate a transductive approach, where the motivation here came from robotics. And it was kind of weird to me that in pick and place tasks, we can define the target position as like XY position. We want to pick and place an object to that target. And then once we change the XY position, suddenly models fail. Because it's the same semantic task, but it's just something is now changing in the specifics. So what we did here is we divided the space of targets. In the blue region are the training target points, and in the orange region are the test target points. And now on the left is a demonstration of the training that's in distribution during training, but models will usually fail on the orange area if we don't do some extra work. So the intuition for how we approach this is converting this out of support problem to an in support, but out of combination. So right now, when the target position goes from blue to orange, and these are unseen targets, so they're part of the input to the model, and now they become out of support. So that is just going to fail because machine learning is not guaranteed to work on out of support data. So we kind of do a little reparameterization, and the intuition is if we know how to go during training from a target that's here to here, then at test time, we could generalize from here to here. And then, so kind of another way to think a bit of it is also kind of like analogies. During test time, we find a training point and use that to extrapolate. Okay, so more formally, instead of learning a predictor H that goes from some X data and predicts some Y data, we learn H on a point X1 and the difference between point 2 and point 1 to predict point 2. And the difference we call delta 2, 1 is literally subtracting X1 from X2. And you can think of X as some kind of latent vector. In the robotics example, we can think of it as a state space. So that is what we use, but it is not limited just to subtraction and to these types of vectors. It could be any representation and any metric that makes sense and that are compatible together. But this is what we use. Okay, so and now we'll keep track of all of our training deltas. Okay, and then we can also make predictions during training for X2 based on a different point X3 and the difference between X2 and X3. And so on. And then at test time, we have this test point that is out of support, and we want to make predictions on X test. And so instead of just making predictions on X test, what we're going to do is we're going to look for a training point that will turn this into an n distribution problem. So if we look at X3 and compare that delta that we get to all of the training deltas, we see that it's not very similar to any one of them. If we take X2 and compare it to the training deltas, it's also not too similar. And then if we take X1 and look at its delta with X test and compare it to the training deltas, we see that it is actually quite similar to delta 2, 3. And so we can select X1 and then the difference between X1 and X test is equivalent to a delta that we've seen during training. So now the prediction over X test is based on X1 and this difference, which is a difference we've seen during training. So now if we think of this as a matrix, so the rows are the deltas and the columns are the X's. Then in the blue region is every combination that we've seen during training, all the X delta X pairs. But then in the green region, these are out of combination points. So these are like X test and delta X test and X1. we've seen X1, we've seen delta X test because it's similar to delta T3, but we haven't seen them in this combination during training. So now we've reduced our problem from out of support to out of combination. And it turns out that under some assumptions, we can get guarantees for when this works well. And then we implement it based on that theoretical work. So the theoretical work was mostly done by collaborator Max. And the idea was we can use matrix completion techniques, specifically matrix factorization, to show that under some assumptions, if the performance on the training distribution is good, then the performance on the test distribution is also good. And so inspired by this matrix factorization, we implement our predictor as a bilinear function. So basically the predictor is bilinear in nonlinear embeddings of X and delta X. So we embed X, the delta, nonlinear networks, and then their inner product is the value that we're trying to predict, and we update with mean squared error. Okay, and going back to this matrix, so the assumptions that we need to promise good performance on the green area is coverage. So we want that green area to have X's and delta X's that we've already seen, just like not in that combination. And we want a specific part of the matrix, the M11 part, to be covered densely, meaning all the X's there see all the deltas and all the deltas see all the X's. Okay, and then the other assumption is about low rank. So we assume this whole matrix has low rank structure, and also that the densely covered area M11 is also low rank. Okay. And in terms of the experiment, so we talked about the pick and place example, and then a typical neural network on the orange region will fail. But then when we use our method, we can zero-shot extrapolate to this new region. In another domain, we want to predict 3D grasping points for various objects from their point plots. So we have mugs and teapots and bottles in various sizes and positions and scales. And then at test time, we have the same objects, but their scales are now out of support. Their XY positions are out of support, and their rotations are out of support. But we still want to be able to predict the grasping point, usually on the handle of the object. And so if these are the ground truth grasping points that we would want the robot to pick up the object from, then a typical neural network would make predictions that are not really feasible, like in the center of the mug. But then with transduction, we can make predictions that are much more accurate. Okay, so then you can ask, maybe in this domain, why not use something that we know about this domain, which like SE3 equivariance. And there are papers that that filled in these things into the models. For example, we compared to this paper. And when looking at SE3, so yes, it puts in rotation and translation, but then not scale. So what happens is that this method will fail out of distribution because we changed the scale, and it will do well on rotation and translation. And in transduction, we're not making any assumptions about the types of invariances or equivariances that we have, and we're trying to learn that from data. And so our model can learn all three. And another example where we can see this is in 1D regression, where we have functions that are invariant, equivariant to translation or neither. And the blue region is the training region and the orange is the test region. And these functions are kind of simple and have some structure, but models still can't extrapolate well. So in black, we see the predictions of a neural network. And their grade n distribution, terrible outside distribution. And when we use bilinear transduction, it works. And so this brings me to the last part. So we realized that bilinear transduction is actually more general than robotics, even though that was the inspiration, and good for just any regression problem. And in robotics, you could also say, well, at least in the domains we tried, you know how to simulate the out of distribution regions. Like you could easily simulate that. But in material science, it's actually quite hard. to simulate the out of distribution domains, because you either have to do that in simulation, which takes a lot of time, or you have to do that in a wet lab, which is also costly for various reasons. So in material science, we're actually not looking at inputs that are out of distribution. We're now looking at outputs that are out of distribution. And the reason for this is because that is what material scientists are mostly interested in. And a little bit of motivation for that is when we want to discover new materials, we care about their intrinsic properties. So for example, solar panels efficiency depends on energy conversion capacity, and efficiency of battery depends on electrode energy capacity, and in drug efficacy depends on drugs binding affinity to a receptor. So if you look at the drug example, what we want to find eventually is a new material that has a property value that's kind of unique, or sometimes called high performance materials. And usually those properties are outside of the range that is known during training. So what we do here is we want to predict the property value y, which is a scalar, given some material x. And during training, we have materials that have y values that are in this gray region. This is the distribution plot of the y values, property values. And then during test time, we get some materials that have property values that are in the red region, and we want to be able to predict them, even though that range is out of the training score. So in this case, we represent materials as vectors as well. And we try this on solid materials and molecules. And in both cases, we represent it with feature vectors that are commonly used in material science, that are composition based. And they include all sorts of information like atomic weight and radius. And you can think of it as like handcrafted features for materials. So again, the setup is slightly different. We're now trying to predict values that are outside of distribution as opposed to input that is out of distribution. Okay, and so since the setup is different, we could also say we don't know if our assumptions hold, because previously we had a very structured type of distribution shift, and now it's unstructured. So it's completely an empirical question. But the intuition is because the representations of materials have information that affects the property values that we're trying to predict, then their difference would also influence their prediction. So in terms of results, this is from a molecules data set where the baselines are in blue and green, the ground truth distribution is red, and our predictions are in purple. And this is for the out of distribution setting. So we see that the distribution over these new higher values that we're trying to predict is not that great for baselines, whereas we can kind of get closer to the distribution. And we can see this even better with parity plots. So these are the three baselines. The x-axis is the ground truth, and the y-axis is the predictions. And gray dots are in distribution, red dots are out of distribution. And ideally, we'd want everything to be on the y equals x line. So in distribution, that happens, but out of distribution, what happens to most methods is that they kind of collapse at that horizontal red line, and they can't really make predictions for y's that were outside of the training range. And if we use radiation transduction, we can go beyond that range. And this is pretty cool for, I guess, several reasons. So first, one thing to notice is that the ChemProp baseline actually has more information than us. It's using more structural information, and also the architecture encodes some equivariances about this domain. And we're not using that, but we can still generalize better. And maybe like a follow-up question here is to ask, are there maybe some kind of invariances or equivariances that people are overlooking right now? And since transduction doesn't need to assume that, it finds it from data, maybe it could be potentially used to find that in cases where people don't know. Then another thing we see is that the true positive rate, the recall, is mostly zero or close to zero, except for our method. And that's great for when we use the ground truth threshold to compute the recall. And since most baselines actually don't pass that threshold, the threshold is usually computed slightly differently. So we'll show that under the common computation, our precision is actually better, because once we lower the threshold, the baselines will get much more false positives. So the way that people compute this threshold is usually they take the max prediction and then like 0.7 times the max prediction, and they look at every material where the prediction was higher than that threshold, and then they compute the precision. And the ground truth threshold is based on 0.7 times the actual like highest 30% performing materials. And so we report this precision for different data sets and properties and different baselines, and we get that ours is generally better or equivalent. And so you could say that recall and precision are important for this problem because we don't want to miss good materials, but also we don't want the wet lab to try out a bunch of materials that don't really make sense. So it, again, like looking at the ground truth threshold for recall, we're doing better, but then looking at precision with this more forgiving threshold, then we're also doing better, which means that if we use this common method, labs won't have to go over many, many potential candidates before finding a material that actually makes sense. Then connecting this idea of bilinear transduction more broadly to the field, then these ideas appear in other places, right? So transduction is a combination of parametric and non-parametric models, because we do have a neural network, but also we do use the training data during test time. And so doing that, and also, again, having the training set at inference, that is something that we have in language models when we use RAG. And then the idea of analogies, looking for training points that are kind of analogous to our test point, that is something that appears a lot in computer vision. And then Josh had a paper where bilinear models, yes, and Bill too, can be used to discover different concepts or compositions of concepts, and then use that model to then combine these concepts in novel ways and generate faces in new lighting, for example. So combining all of these ideas together and under some assumptions, in our work, we show that out of distribution data can be reparameterized to be in distribution, and then out of combination can do better when using a bilinear predictor. And so thinking about the future, so yes, a lot of the effort today is about scale, and yes, maybe it will be enough for many things, and I like to keep thinking about the things that it might not be enough for. So adaptation to new tasks and personalization, and again, when we deploy robots in specific homes, and how do we adapt to specific users, assuming that we won't be able to anticipate every single scenario in advance. And then performing similar tasks in a changing world. So if a semantic task has different instances, how can we still be able to perform it? Like, why do we need to cover all the space of XY targets when when we as humans don't really have to do that. Okay. And in terms of directions that I want to keep thinking about, so I want to think about reasoning and generalization in classic AI scenarios like robotics. And I think it's also interesting to think about AI for science, where there's not a lot of high quality data. So being able to actually generalize when there's not a lot of data could actually be very impactful in this case. And then another thing, look at the large models and look at what is that maybe 5% that's still missing from those large models, and why does that happen, and how can we bridge that gap? So acknowledgements. So Pulkit, thank you for accepting me to your lab and allowing me to witness and also be a part of you building your lab. I think you've done a great job with bringing excellent people and really creating a culture where people are friends, and we have lab retreats and socials and birthday celebrations. You always make sure everyone has what they need to do their best work, whether it's equipment or conferences, or collaborations or anything. And you've always encouraged me to think more critically about work and contextualize things and tell good stories. So I learned a lot from you. And also personally, you've been very supportive with during COVID and everything. Josh, first time I met Josh was at a computer vision summer school in Sicily when I was doing my master's. And you also gave a talk there, and it was extremely inspiring. And the way you think about AI from the cogSci lens is always super inspiring. And we didn't get to talk a ton because you have a lot going on, but every time we did, you're always very kind, very supportive, and again, very inspiring and encouraging. So thank you for that. And Jacob, you were on my RQE, and you gave excellent feedback there and during the committee meetings. So you think super fast, and you have great questions and great thoughts on how things are related to each other. And I really appreciate all your feedback. And you really care about students and making sure you can support them the best way. So thanks. Then I want to say thanks to Boris and Andre, who I worked with during my first year and kind of gave me my first shot at MIT. And Boris is extremely kind and supportive, and Andre is brilliant, and they were wonderful to work with. Then Josh, thanks also for introducing me to Tianmin. Tianmin was a postdoc here, and now he's at Johns Hopkins, and he's a great mentor, and he knows a lot, and he has a unique way of thinking about things. And I really appreciate his support and collaborating with him and learning from him. And then Abhishek and Max were also postdocs here. Now Abhishek is at UW, Max is at CMU, and two of the most brilliant people I've ever met. A big part of this thesis was done together with them, and thanks to them. And I really appreciate the time I worked with them. Then got to work with a bunch of awesome people, some are here, and at MIT and beyond. And that is really the best thing about MIT, that people here know so much and are willing to share and work together. Okay, then the Improbable AI Lab. So lucky that we don't have the same photos. So I think on the left is the only lab retreat where you actually saw fall colors. Usually it looks like in the middle. But yeah, again, thank you, Pulkit, for creating an environment where people actually got to kind of step away from their computers and know each other a bit more. And then outside the lab, the EI community has been great. Some Friendsgiving dinners and other apple picking and other events. And then there are friends who made Boston feel like home. So I'm super grateful for all their support and humor. And then my parents. So when I was a kid, my parents were doing their PhD. And so naturally, I thought everyone had to get a PhD. And then I was very worried. So I asked my mom, it's okay that I don't know what I want to do my PhD in. And then she reassured me when I was 5 that it's okay. So thanks, Mom and Dad, for still reassuring me and encouraging me to believe in myself and keep going. And then my brother is one of my best friends, and I'm super grateful for his presence in my life. And my grandmother, it's hard to kind of be away from grandparents as they get older. And my grandmother especially had like a few difficult years, but every time I talked to her, she would encourage me, and her belief in me kind of kept me going. So, okay. Then my husband, he sacrificed the most during my time here. Like here you can see he's having a hard time, and after I dragged him to Hawaii. But for real, he's a doctor, or a real doctor, and he was supposed to do his residency in Israel, but he came to the US with me and worked really hard to get into a residency program here. And he's been super supportive before deadlines, did a lot of cooking at home. And so I'm very grateful for his support, so thank you. And then last but not least, this is our daughter. And she started out like this and turned into this during the last year and a half. And so to kind of quote Ming Ha in his job talk, she's the best AI system that I've ever built. But outside of that, she just is amazing and really keeps me grounded and reminds me of what's important in life. Okay, so with that, thank you.
Well, now we have time to grill Aviv. One last time. Any questions? An excellent job, Aviv.
Thanks.
No one has any questions.
I'm also looking at the chat if anyone on Zoom has just.
Dan, you want to
I
ask
guess,
one?
yeah, I'll ask one. So sort of the takeaway from your work was that like we parameterize a lot of problems as bilinear sort of structure, which allow us some audio generalization, which is very impressive. But at least in my experience, there is a downside to any bilinear structure, which is usually make training much harder because you have this like, again, bilinear dependencies that is usually make the problem more complex and so on and so forth. I wonder if this difficulty is something that you encountered during your work in terms of training instabilities and stuff like that. And like, if you see a way to overcome that.
Yeah, good question. So in most of in the domains that I showed empirically, we didn't have problem training that, but also there's a big importance for how you choose your training points. So in all of the domains, we just randomly chose pairs to train on, except for actually the example with the mugs and the teapots, where during training we did use privileged knowledge, where we only want to compare teapots to teapots of different sizes and orientations and scales, and only mugs to mugs. And then if we compare teapots to mugs, then things start to get weird or complicated, or you might be able to overfit, but then I'll generalize. So depending on how complex your data or how much variance you have in your data, then one way to overcome that is using this privileged knowledge during training. But then turns out you don't really have to use that during test time, because if you're just looking for a training point that gives you the difference that is with the most within distribution, then you'll eventually, if you get a mug during test, it will find a training mug because that's closer to what it's seen.